start. Good morning, good afternoon, or good night. It is really a pleasure to be here today with Professor Naoki Shinohara-san. So it's really a pleasure to be here today. It's, with one of the most well-known persons on far field and long-range wireless power transmission in the world. So Professor Naoki Shinohara received his bachelor degree in electrical engineering and the master and PhD programs in Kyoto University, Japan in 1991, 3, and 6. He was a research associate in Kyoto University from 96, and from 2010, he has been a professor in Kyoto University. He has been engaged in research on solar power stations, satellites, and microwave power transmission systems. He's an IEEE fellow, a NERSI fellow, and he was the IEEE MTTS Distinguished Microwave Lecturer from 2016 to 2018, and he is a IEEE MTTS ADCON member, and he also belongs to the IEEE MTTS Technical Committee 25 Wireless Power Transfer and Conversion. Well, among a lot of other activities, Professor Naoki Shinohara is really well known for a group of books on wireless power transfer. So if you are interested, and if you are listening to us today, if you are interested in looking and learning more about long-range wireless power transmission, I really advise you to see the vast line of books that Professor Naoki has from different editors. And I think it's really a pleasure to be here. So today we are going to talk about filling in the missing link in radio wave technologies. So wireless power and wireless applications, inductive WPT and radiative WPT, millimeter wave wideband WPT, and gigawatt narrowband beam WPT. So I think it's going to be a great talk and a great discussion. So in order to start, welcome, and why did you decide to start working on this field? If you can share with us. Thank you very much.
Yeah, thank you so much. Thank you for introduction. So I'm very glad to be here. When I was a bachelor student in Japan, usually fourth grade of the bachelor course, we Japanese students must write a short thesis for graduation. And at that time, I attended the meeting for young students in Kyoto University. And at that time, my boss, Professor Hiroshi Matsumoto, showed me what is a wireless power transfer and what is a solar power satellite or a space-based solar power. And when I was young, so I was very surprised. What a great technology, solar power satellite, SPS. And I was very shocked. I hoped I would like to join this laboratory, Professor Matsumoto's laboratory. And from my student time, bachelor course and master course and PhD, and after start working in university, I keep the same research, wireless power transfer only. So if I miss the opportunity to hear the explanation by the Professor Matsumoto, I'm not here. So it's it was a great opportunity for me to join this research field for the wireless power transfer. It's 34 years ago.
Yeah, I'm so sorry. I think my my Zoom.
No.
But I'm back. So yeah, it's really interesting that you start working on these activities since your bachelor and master program. So it's a long
Yeah.
path to this. So what were the initial solutions that you foreseen for wireless power transfer. So what are the main, let's say, human society aspects that you plan to resolve with this technology?
Yeah, thank you so much. So in my student time, my research was not exactly meaning my research was not a wireless power transfer itself because research area of my boss, Professor Matsumoto's research was space plasma physics. So he was a scientist of the space plasma. And from this viewpoint of his research, space plasma physics, he studied the research of the solar power satellite and additionally wireless power transfer. So in my student time, half of my work was space plasma physics related to the wireless power transfer. And at that time, my boss carried out some experiment of the space experiment to check, to measure the counter effect of the high power beaming microwave with space plasmas. And so slightly, so day by day, I changed my research topic from the physics to the engineering. And at that time, at first, I developed the very tiny rectangle for his demonstration. For example, to fly the airplane only by the microwave, or to demonstrate the target detecting and beam forming technology in my first research times. So at that time, so I was not an engineer. I was a scientist of the space plasma physics in my student time. But day by day, I changed my research from the science and engineer. And recently, of course, as you know, I promote the long-range wireless power transfer. And from this background, my research area is not only the one topic. So, for example, some professor, their research topic is the antenna itself only, for example, and the other professor develops a rectenna or rectifier only. But from my background, my research topic is very wide, covers a very wide area, and I developed a rectenna, and I developed a beam-forming antenna, and I developed a magnetron, for example, to reduce the cost of the microwave power system. So, in this meaning, I think I'm very lucky to consider all about the wireless power transfer. And recently, not only the long-range far-field WPT, but also the near-field coupling WPT, I cover my research to promote the at-last solar power satellite, but at first from the near-field WPT commercial system to the wide beam, like a Wi-Fi WPT system recently. So in this meaning, I'm very lucky to consider all about the wireless power transfer. I think so.
Thank you very much. So, from your perspective, do you think the dream of Tesla, which is to remove the cables, the power cables, is very far away, or do you think in the soon in the future, in 5 or 10 years, we will see this technology being applied in our houses, in our cities? How do you see the evolution of this technology in the next 5 to 10 years?
Yeah, thank you so much. So I think within a few years, we can realize the dream of Tesla because, as you know, Tesla's dream is a world system. Every time we can receive the power everywhere. But in this meeting, now my colleagues, my friends are promoting the wide beam WPT and the near field WPT are all WPT technology in the world. And we can now we can receive the very weak power by the microwave to provide it the everywhere. And so in this meaning, we can drive the IoT sensor, very weak powered sensor everywhere. And so I think it's the same as a dream of Tesla. But at last, we can transmit a very high power, for example, gigawatt power from the space to ground, 36,000 kilometers. So in this meaning, we can overcome the dream of the Tesla within 20 years, 30 years, I hope so. And so day by day, this WPT technology is produced in the world. So from the near field WPT and wide beam WPT with a milliwatt power, and so at last, we will transmit the gigawatt power from the space. And it is involved in the dream of Tesla, and we can overcome the dream of Tesla within hopefully 20 years. I think so.
Yeah, that's good. And recently I saw that in the United States they are actually moving to laser wireless transmission, mainly for space environments. Um, uh, and not to millimeter wave wireless power. So, what is your opinion on that? What do you think are the main advantages or disadvantages of using laser versus using radio frequency millimeter wave links?
Yeah, thank you so much. Yeah, I agree. So laser power transfer, optical wireless power transfer is a very good technology to focus the wireless power into the one receiver. As you know, we have a limitation with the maximization and the Friis transmission formula. And based on the Friis transmission formula, beam efficiency from the transmitting antenna to the receiving antenna is limited, limited by the antenna size and the distance and the frequency. It's very simple. So when we would like to increase the beam efficiency, as an engineer, what we can is only to increase the frequency because distance is decided and we would like to reduce the size of the antenna. So only the way to increase the beam efficiency or to reduce the size of the antenna is frequency. In this meaning, optical or laser wireless power transfer is best to reduce the size of the antenna and to increase the beam efficiency with a highest frequency. But it's unfortunate that just now we don't have a good beam control or beam forming technology in the optical system. They don't have any phased array antenna like a microwave or millimeter wave. So important technology in the long range WPT is beam forming or target chasing technology because user and the transmitter is separated and we cannot detect the position of the user. In this meeting, we need more time, a long time to develop the phased array antenna in the optical system. But as I told you, I'd like to realize solar power satellite or gigawatt beaming system within 20 years. So in this meeting, now I think microwave beaming system or millimeter wave beaming system is better than the laser power transfer system. But distance between transmitting antenna or receiving antenna, for example, like on the moon, we can apply the laser power transfer to reduce the size of the antenna. It's a case by case. But if distance is very long, 36,000 kilometers from the geostationary orbit, I think we cannot apply the optical laser power transfer system now. But in future, of course, it's a competitor of the millimeter wave and laser power transfer. I think so.
Yes, definitely. And another question that I have is we when we talk about space-based solar power, we talk about geostationary satellites. How do you see other alternatives like using LEO So satellites that are lower orbit, or using other technologies like HAPS, so the high altitude platforms. I know that you have done some work in the past with some of these UAVs somehow. Can you talk a little bit about that?
Thank you so
How
much.
you see these different
Yeah.
technologies?
Yeah, thank you so much. Why we choose a geostationary orbit 30,000 kilometers above, we would like to stay the solar power satellite in one point. It's a geostationary orbit. But at the same time, the weak point of the solar power satellite when we decide the distance, and we choose a one frequency as a millimeter wave or microwave based on the Friis transmission formula. It's easy to calculate. It's easy to estimate the size of the antenna. And size of the antenna with a very high beam efficiency become the over 2 kilometer size of the antenna. So a lot of people consider SBSP or solar power satellite is very huge and we cannot develop it. So instead of the geostationary orbit, to increase the beam efficiency and to reduce the size of the antenna when we fix the frequency, of course, easiest way is to reduce the distance. In this meaning, some of my colleagues, my friends, propose the SBSP in LEO, low Earth orbit, or of course, between the weak part WPT and long SBSP, we propose some application of the beaming WPT to the flying HAPS or flying drone or the other. It's a very good missing link between the geostationary orbit solar power satellite and weak powered beaming commercial system. But the other weak point in LEO SPS occurs. So in the LEO satellite, they move about 20 minutes in every once in the rotation on the Earth. So solar power satellite SBSP is a power station. So everywhere, every time we'd like to receive the electricity from the space. But when we put the solar power satellite in LEO, he moves every time. So in this case, we must put a lot of satellite, solar power satellite, everywhere in the LEO and like a GPS satellite. So, of course, we can reduce the size of the satellite and the size of the antenna in LEO solar power satellite. But instead of to reduce the size of the antenna, we must increase the satellite, number of the satellite. So in 90s, Japanese group proposed a LEO small SPS system named SPS 2000. At the time means 19th. We would like to launch this small LEO satellite until the 2000. So it is named SPS 2000. And at that time, receiving point is on the equatorial countries. And in every equatorial countries, we transmit the microwave power from the LEO satellite. It was a Japanese idea. But unfortunately, we could not launch this small satellite. So, but we Japanese group consider to launch the small satellite and formation flight or the constellation satellite, solar power satellite. But it includes a pros and cons. From the viewpoint of the wireless power, it's better. We can reduce the size of the antenna and we can reduce the size of the satellite in LEO. But as a power station, it's a very weak point. How to transmit the power every day and every time from the LEO. So it's very difficult problem.
Yes, For sure, for sure. But do you think the future of solar-based solar power will be more on this LEO or very low Earth orbit, or more on the geostationary? How you see this competition? Do you think so? The countries which I believe Japan, China, US, UK, they are actually looking to this square kilometer array geostationary antennas. Do you think this will be a reality, or do you think it's still a little bit of science fiction and we still have a lot to work until we get there?
Thank you so much. So I think it's a realistic parameter because it's only the size of the it's only the size problem only. And so as you know, we would like to develop the phased array antenna, and the phased array antenna is consist of the small lot of small antennas. And when we increase the number of the antenna, at last we reach a 2 kilometer size of the phased array antenna. Of course, we have some problem to control the phase with a very huge number of the phased array antenna, but it's a very small problem, I think so. So with a phased array antenna technology, and it's the same on the solar cells. And a solar cell is consist of the very small unit. And when we increase the number of the unit, it's easy to create a very huge solar cell, like ground system. We have a gigawatt solar cells on ground. So in this meaning, problem is only a size of the antenna and the solar cell. So in this viewpoint, I think it's not a science fiction, and we can develop the huge size of the phased array antenna with a good engineering, good technology. So someone consider when solar power satellite will be launched, we must launch a very huge number of the launch system. Even if we choose Tesla's US commercial launch system. So a lot of people, including engineers or the professors, consider it's not it's impossible. But we are engineer, and the problem is only the size only. So as an engineer, I believe we can do it. There is there is no problem. It's too much. But when we consider how to build huge size of the antenna, we can realize it within 20 years or 30 years. I think so. But this technology is related to the weak part WPT or the other small application. Technology is the same. Technology is the same. Difference is only a size of the beamforming technology. Now we don't have a beamforming technology as a commercial system. We only provide the wireless power. But in the next step, as a commercial system, user require much power, for example, to charge the mobile phone. And in this time, next step, we need a beamforming technology, and it's same technology for the solar power satellite. I think so. In this meaning, from the weak part wide beam WPT to the gigawatt solar power satellite, we can apply the same or the similar technology of the long range WPT, and so it seems to be strange, but it's same technology. I think so.
No, thank you very much. And I agree with you. It's merely an engineering problem that we have to resolve. Another question I have for you, and I saw a lot of discussion about this. What do you think is the best transmission approach? Is using reflectors? Is using active antenna arrays? Is using dielectric lenses or metamaterials? What do you think is the best option for the transmit antenna array? Do you have a preferred solution?
Thank you so much. So as I mentioned, best way for the future WPT system is a beamforming antenna system with a simple phase array system. This keyword, simple, is very important because antenna size will be very huge. So, of course, I expect the metamaterial, meta surface, for example, to increase the beam efficiency. But of course, I believe the future of the meta surface. But in physics, even if we can reduce the size of the antenna with help of the meta surface itself is a same very huge size we need. So in this meaning, we don't need a very special meta surface technology. It's the same technology with and without meta surface for the size of the antenna itself, including a meta surface. And 36,000 kilometers beamforming system, we need a very high accurate beam forming and beam controlling system because a target of the receiver on the ground will be within 2 kilometers. You think 2 kilometer size of the ground system is very huge, but compared to the 36,000 kilometers, this target is very tiny. So we need a 0.0001 degrees beam accuracy. So in this meaning, we cannot apply the reflector parabolic antenna system or the other mechanical beam controlling system. So beam forming or the phase array antenna and simple phase array antenna is very important, I think, because we have to reduce the cost of the solar power satellite. Of course, as a commercial system, in next step, we need a very simple and cheap phased array to provide the wireless power into the one user. So this simple is one keyword for both for the commercial system and the solar power satellite. I think so.
Okay, yeah, thank you very much for your explanation. It's very clear. And I know you prepared some slides about your works and some of your work. If you want to show those slides, and we can talk about them also.
Yeah. Yes. Can you see my screen?
Yeah, I can see your screen.
Yeah, so thank you for giving a good opportunity to explain my research and the future of the wireless power transfer. So I heard this opportunity to explain my research and the power field WPT. What is the best title for this podcast? So I found this keyword filling the missing link in the radio wave technology. So as I mentioned, sometimes gigawatt solar power satellite application and milliwatt wide beam WPT is on the same field. We can apply the same technology. And additionally, there are a lot of now commercial inductive WPT wireless charger for the mobile phone in the world. And theoretically, inductive WPT and radiative WPT is not a different system, I think. And so additionally, power and application, including commercial system, is the same technology. It's my policy. So based on this viewpoint, I'd like to briefly my research with some materials. So this is my history, R&D history in my life. So from the 80s in Kyoto University, my boss, Professor Matsumoto, studied this research. And as I mentioned, he was not an engineer of the radio wave technology, and he was a scientist of the space plasma physics. So in 80s, he carried out the space rocket experiment to measure the counter effect from the space plasma by the high power microwave. It is named the Minix rocket experiment. Of course, I was not in Kyoto University and I was a junior high school student at that time. But this is a very good memorial experiment for the wireless power transfer. It is a world first WPT experiment in space. And it is 1992, he changed his mind from the science to the engineering, and he carried out the airplane, microwave-driven airplane experiment named MIRAX. And I was a master course student, and I was very lucky to join this big project with my boss. And so I was very surprised and I enjoyed this big project. And in this experiment, we adopt the phase array antenna to control and the beamform and to chase the flying airplane. So in my understanding, this is the world first WPT experiment with a beamforming antenna, phase array antenna in the world. So at that time, I joined it as a one student in this experiment. And after success of this MIRAX experiment, we, Professor Matsumoto and I and my colleagues, carried out a lot of WPT demonstration and research. And recently here, I changed mine from only the engineer to the business of the wireless power transfer. I think, of course, my dream, solar power satellite or the space-based solar power is a very excellent future dreams. I think so. But if I push the SBSP only from the university, there is a very few people only to agree this dream. So we need a technology based on the business as a engineering. I think so. So after the revolution of the MIT's resonance coupling 2006 and 2007, I promote the business of the wireless power transfer, mainly the wide beam WPT recently. And for example, this is a Japanese newspaper, and with Panasonic, a very big company in Japan, we developed a commercial WPT system. And so now Panasonic is promoting the WPT business. Of course, they don't mind the solar power satellite. Now, they only consider the business, WPT business only. But as I mentioned, all WPT technology, including resonance coupling, wide beam WPT, and gigawatt beaming WPT, are based on the same theory and technology of the radio wave and electromagnetic field technology, I think so. And I put the all movies in the YouTube. Please check our YouTube channel, SHINOHARA Laboratory, if you are interested in. And
No,
so,
thank you. If
yeah.
Can you go to the previous slide? So, yeah. So thank you very much, because this gives a clear picture of how the evolution of your work is, and thanks for the QR code. I think it's also very interesting to see what. But I have one question here for the Panasonic. What
Yeah.
is the distance between the transmitter and the receiver, more or less?
Yeah, here you can see the figure of the WPT system. It's an in-room system. In this meaning, distance between the users and the transmitter is only within 10 meters or 5 or 6 meters only. Of course, it depends on the technology, and additionally, it depends on the radio regulation in Japan. So, of course, technically, we can transmit the wireless power to the, for example, 50 meters away or the other. But as a commercial system, we have to consider how to reduce the cost and how to suppress the interference and how to protect the human body. It's a safety problem. And we Japanese discuss a lot how to coexistence with WPT system and wireless communication system and the human being or the other. So best solution of the commercial WPT is a very short distance WPT within 10 meters. It's from the viewpoint of the cost and the viewpoint of the size of the antenna or the other safety or the interference or the other. So in Japan, commercial WPT system is mainly within a 10-meter distance system just now. But we keep a discussion with the government, and we would like to extend the distance on the WPT system in near future. And of course, we have a technology to extend the distance. So if we can establish a new radio regulation, not only in Japan, but also in the world, we can extend the distance over 10 meter, 20 meter or 30 meter. But just now, based on the regulation and based on the technology and the cost problem, distance is only 10 meter.
Nice. Thank you. Thank you very much. Yeah, if you can continue for.
Yes, thank you so much.
Yeah.
So this is, of course, as I mentioned, my R&D topic is system of the WPT, and I cover a lot of technology, rectenna, magnetron, or the other. But recently, what's the best my R&D technology is I consider, and so beam forming technology is our very good technology, I think. So from the end of the 90s, for example, in my laboratory, we developed some kind of the phased array antenna. And at that time, about 30 years ago, I developed a 2.45 gigahertz retrodirective phased array antenna. And at that time, and day by day, year by year, our technology becomes better, and we increase the frequency from the 2.45 and the 5.8, and at last year, we developed a 28 gigahertz phased array antenna. So for example, and so as I mentioned, we developed the magnetron phased array to increase the efficiency and to decrease the cost of the phased array antenna. As you know, we have a very good phased array antenna, not only for wireless power transfer, but also the remote sensing or the other. But cost of the phased array antenna is very, very expensive. So we consider how to reduce the cost of the phased array antenna. And we propose some kind of the method to reduce the cost of the phased array antenna. And so about maybe the 25 or 20 years ago, we find the magnetron phased array antenna technology. It's originally from the William Brown technology. He developed a very similar magnetron phase controlling system in 70s. And we revised and we updated this magnetron system. And for example, this figure, in this figure, we developed a magnetron phased array for SWIFT. So William Brown could not realize the SWIFT simultaneous wireless information and power technology because magnetron is originally the generator only. Magnetron is not the amplifier. It means it's very difficult to add the information magnetron cannot create a modulated wave. So William Brown did not realize this SWIFT magnetron, but we, Kyoto University, developed a SWIFT magnetron phased array system to drive the TV to watch the DVD movie. for example. So of course, now we cannot apply the magnetron phase array because we transmit over kilowatt microwave power. I agree it's a little bit dangerous system for human body. But in future, for example, to fly the drone or to provide the power to the flying harps or the other, we need over kilowatt, or sometimes for example, for harp system, we need a megawatt microwave power. At that time, this magnetron system can be applied for this drone and harp system, I think so. And in parallel, we propose and develops a very interesting novel beam-forming algorithm and technology to increase the beam efficiency. This keyword is very important because, as I mentioned, we have a good technology for a good technology of the phased array antenna for remote sensing. It means there are a lot of excellent research for the beam forming. But almost all technology of the phased array antenna and beamforming technology is mainly to suppress the side lobe only, or to increase the front gain only, and to increase the beam to increase the sorry. But for a WPT system, in our viewpoint, we need a good beam efficiency. It means not only the front gain, but totally at the receiving area, we would like to increase the power of the microwave. So in this viewpoint, we propose some novel beam forming algorithm or technology. For example, high efficiency beam by quasi amplitude taper by the phase control only, or we propose some interesting novel algorithm of the random array. If we apply the random array to reduce the grating lobe, this decreased power from the grating lobe will be converted to the side lobe mainly. It's a usual way in the random array. But our proposed system, we can increase the beam efficiency both to reduce grating lobe, and we can convert this grating lobe power to the main lobe by our proposed random algorithm. And so we propose some retrodirective system, and recently we propose a flat beam in the Fresnel field to increase the beam efficiency, as I mentioned. And in this algorithm, we can increase both the beam efficiency and conversion efficiency as a receiver, rectangular arrays. So this beamforming technology we propose is a very interesting technology, mainly for the wireless power transfer, I think so. This is our sales point in my laboratory for the wireless power transfer recently.
So thank you very much for sharing this with us. The 2024 28 gigahertz phase array, how many elements do you have in that phase array?
In this system, I forgot the total number of elements, but so this system is a 75 dBm transmitting system. So with this 28 gigahertz system, we drive the small IoT sensor at 10 meters away. And so in this system, here you can see we apply the waveguide-based low-cost phase array system. It means we don't use the pin diode, the phase shifters in this system, because pin diode, phase shifter, it's very cost system. So we consider how to reduce the cost and how to develop the very simple phased array antenna. As a result, we propose a waveguide based, and we add some very small motor to change the size of the waveguide. And based on this very simple waveguide system, we can control the beam direction with very low loss. And so even if we choose a 28 gigahertz very high frequency, we can develop a very low cost and very low loss phased array antenna.
Very nice. That's very impressive, and also the flat beam is amazing. So yeah,
Yeah,
congratulations.
thank you so much. So it's our original technology because usually antenna people consider the antenna only. But as I mentioned, we consider the WPT system. In this meaning, totally we would like to increase the efficiency of the WPT system. It means it involves a beam efficiency and a circuit efficiency. We must increase both. But even if we create a very good beam form, as a viewpoint of the antenna, it's best because we can increase the beam efficiency. But this beam form is not suitable to increase the conversion efficiency at the receiver. So we propose this flat beam form to increase the beam efficiency and conversion efficiency at the receiver rectifier arrays. So in this viewpoint, this is a very interesting, I think so.
So and you bring all this technology to space-based solar power, correct? So
So as I mentioned,
yeah.
my dream is a space-based solar
Yes, yes,
power.
yes.
But in the next step of the commercial system, we can apply this beamforming antenna. For example, this figure indicates the in-room WPT system, and this is originally from the US startup company. And when even if we put the transmitter phased array antenna in room, in this case, there are a lot of walls as a reflector. And in this situation, usually we cannot apply the retrodirective beamforming and target detecting antenna because we have a mulch path in room. But this patent of the US startup company told us we can apply this retrodirective system in room and mulch path system. And but I had some doubt in their patent. So my student carried out experiment and a computer simulation and experiment, and we found their patent is true. And we can apply the in-room and multipath beamforming and retrodirective system. And additionally, of course, we updated this technology, not only on the phase control, but also the amplitude control we added. But so this beamforming technology can be applied for the commercial system in next step. So I think this all technology can be applied, all WPT technology for commercial system and SBSP or the HAPS driving system or the other. So there is no missing link, I think so, in this technology.
Thank you. Yeah, I agree. That's very good.
So
I think yeah, you can continue if you want.
Thank you so much. And so, as I explained a lot, I don't have to explain more. This is an image of the sort of SBSP. And fortunately, in the world, now there are some ongoing projects in US, in Japan, and in China, of course, in Europe, etc. So this solar power satellite can realize the bright future without any carbon dioxide emission because this is a solar cell system. And this is a very stable power station, even in the night and even in the rainy day. Because of geostationary orbit, there is no night, and microwave is not absorbed in the rain or the air. So if we put the solar cell on ground, unfortunately, in the nighttime or rainy day, we cannot generate the electricity. But SBSP, we can generate the microwave and the electricity even in the nighttime and rainy day. So in this meaning, this SBSP, based on the long-range WPT technology, we realize our bright future, and we can decrease the temperature. Today in Japan and in Europe, it's a crazy temperature, over 30 or over 40 centigrade recently. It's a crazy days, and we have to protect. We have to reduce the carbon dioxide, and we have to revise the global warming problem. But now, unfortunately, there is no best solution. Even if we have a solar cell on the ground and wind power, or sometimes atomic power or the other, it has a pros and cons. But this SBSP with WPT technology is a best solution to realize the very stable power station and electricity without any carbon dioxide. So WPT or the microwave or millimeter technology can solve the global problem. I think so. So this is an explanation how to connect the commercial system and the solar power satellite. Of course, the scale of the WPT system is very, very different. So this is the discussion history of the WPT regulation. As a commercial system, of course, this radio wave regulation is very, very important. And of course, we need a regulation for the SBSP in future. But almost all people consider, so as Nuno mentioned, SBSP is like a science fiction, and we don't have to discuss now. But for the future, we need a regulation or the standard for the future solar power SBSP. So at first, in the end of the 70s or the end of the 20th centuries, NASA or the JAXA, Japanese Space Agency, proposed some document to create the WPT regulation for the SBSP at that time. But even now, they don't mind the regulation for the SBSP. At that time, they didn't mind the necessity of the WPT regulation for the future SBSP. So we keep this document under question only at that time. But after the MIT's revolution, as I mentioned, so we come back the discussion to create a WPT regulation. And for example, 2017, at first, ITUR, International Telecommunication Union, established and published the recommendation for the coupling WPT, including resonance coupling. And they used the same question for the SBSP at first. Of course, they considered it was very easiest way to start the discussion for the coupling WPT. Of course, it's the same WPT technology, I think, and gigawatt long distance SBSP WPT, and contactless very short distance coupling WPT, they consider it's the same WPT technology. So they started the discussion from the document question for the SBSP, and they reached agreement to publish a recommendation for coupling WPT 2017. And in parallel, we update the discussion of the far-field long-range WPT. And at first, 2022, we published a recommendation for the wide beam, very weak power and multi-user WPT. Of course, at that time, it's very far far to the SBSP gigawatt beaming WPT. But based on this recommendation and the hot discussion, the other group consider we can come back again the SBSP. So 2023, UK and Saudi Arabia group resubmit the document to discuss about the SBSP. So this is a very good rotation from the coupling WPT, wide beam WPT, and the gigawatt WPT for the WPT regulation. And additionally, in parallel with Japanese published a new formal national radio regulation for the wide beam WPT. And fortunately, we could excite the discussion of the WPT regulation. And from this year, I will propose the IEEE standard discussion in the IEEE Standard Association. I will submit this document within a few days. And so I would like to involve all radiative WPT, not only for wide beam commercial WPT, but also the long range beaming WPT. I hope so. So if I choose only the solar power satellite research, I could not excite this hot discussion for the WPT system totally. But so I excite the even coupling WPT within this with this 20 years, I could go back the discussion for the SBSP again. So I think I can feel the missing ring between the coupling WPT and the wide beam commercial WPT and the long range SBSP. And SWIFT is a very important technology. So it involves the all radio wave technology into one, I think so.
Thank you very much. I think this is great, and what you are doing for standardization of these technologies is a must. And thank you for your work on these activities. It's very, very important.
Thank you so
For
much.
sure.
Yeah, and this is maybe the last slide. So as a professor, I would like to explain how to match the theory of the old WPT. Sometimes we consider coupling WPT and radiative WPT as a different technology. But I think it's one. It's the same technology of the inductive WPT, coupling WPT, and the radiative WPT. Because for the coupling WPT, we use a coil only. And but this coil becomes an antenna when we increase the frequency. And so MIT's resonance coupling, they use a resonator, as they mentioned. But I think, antenna is a radiative resonator. So in this meaning, only a difference between the coupling WPT and the radiative WPT is frequency and how to consider the resonator. For the coupling WPT, we use a non-radiative resonator, but we use a coupling technology in the coupling WPT. But when we increase the frequency, this non-radiative resonator becomes a radiative resonator of the antenna. So when we use a very low frequency, there is no resonance, and coil is only an inductor. But when we increase the frequency, this coil becomes a non-radiative resonator for the coupling WPT. And at last, this resonator becomes an antenna, and power, electromagnetic power becomes an electromagnetic wave, and we can transmit the power. So this technology all based on the Maxwell's equation. So I think theoretically, near field coupling WPT and radiative WPT are the same and seamless. So in near future, we can develop this seamless WPT technology. If we put, for example, mobile phone in the very close point of the transmitter, this transmitter and mobile phone will be coupled electromagnetically. And when we put the mobile phone, for example, in our pocket, and distance becomes very far. In this time, we apply the same transmitter, but in this case, this transmitter can transmit the radio wave, for example, microwave or the other, to charge a mobile phone. So I think in near future, we can use the near field WPT and the far field WPT as a seamless wireless transmitter. Of course, theoretically, we can apply the coupling near field WPT even in the SBSP, because based on the theory, so 36,000 kilometers is in the near field. If we choose a very, very low frequency, it's a theoretical trial, but theoretically, we can apply the near field WPT even in the SBSP. And I think this is originally from the dream of Tesla. As you know, Tesla promoted the both technology of the near field and far field WPT, as you know. And his proposed world system is based on the resonance coupling. And his dream was to provide the wireless power based on the resonance coupling. So in this meeting, on the Earth, he would like to provide the power wirelessly based on the coupling WPT. It's his proposed world system. So theoretically, we can do it. So there is no missing link between the coupling WPT and far field WPT and SBSP, theoretically. It's my dream of the
Yeah,
future.
thank you very much. This is a very nice view of this technology. But when you increase frequency, you are assuming that coupling will continue to exist, right? So coupling will
Ah,
exist all the time, or not?
yeah, of course. Here you can see. So there is no exact borderline between
Yes,
the
exactly.
coupling and the radiative.
Yeah.
So, for example, my friend, Japanese professor, wrote a paper how to change the coupling and radiation, even in the same antenna system. And when we close the receiver in the near field, so some there is no there is some combination between the coupling and the radiation. So there is no good explanation how to match this coupling and radiation. So we need more research to explain this mid area, missing link area of the coupling and radiation, I think.
Yeah, I understand that. Yeah, but I think it's a very good idea so that we can have a continuous and an integrated view of the wireless power transfer technologies. I really like it. So I think we are running out of time.
Mhm.
I think you have one last slide, but my question is how you see the future of these technologies. How you see where we go in the future for
Yeah,
for
thank you
for
so much.
now.
So my keyword of the dream is electricity like the air. So it means air is most important for animal and human beings. If there is no air like a space, we cannot live. But we don't mind the air itself usually. So I think electricity is a very similar. It's most important for our human being, our life. And now we need a power line or the battery, and we usually mine where the battery is and where the power source is to use electricity. But if we have a technology with a wireless power, including a coupling and wide beam and narrow beam long distance WPT, we don't mind where the electricity is. So unconsciously, we can use the electricity. So in this future, electricity like the air, and I think future children doesn't understand what the electricity is, because everywhere, every time we use electricity without any consideration of the power position of the power source or the battery shortage or the other by the WPT technology. So this is my future dream, and a wireless power society and electricity like the air. Most important, air and electricity can be provided unconsciously, and children cannot understand what electricity is in future. It's my dream.
Yeah. Yeah, thank you very much. I think it's a good dream. So that we don't think really where the power is coming from, and similar to what Wi-Fi is doing. So children no
Yeah.
longer understand where the data, the
Well, recently,
communication comes from. Yeah.
yeah, recently, so people doesn't mind the antenna, and my friend my friend doesn't know the antenna itself because now we cannot see any
Yes,
antenna on the mobile phone.
on the phone. Yeah.
So some people doesn't know the antenna itself. So I think in future people doesn't know the electricity itself.
Exactly. Yeah. Thank you very much, Professor Naoki Shinohara. It was a really pleasure to have you here. I think we run our time, but I think we could stay here for more 1 or 2 hours discussing this interesting topic. And I this concludes this vodcast and this podcast. So thank you very much for attending, and we will continue to have other podcasts. And again, thank you, Professor Naoki. So
Thank
it's
you so
I
much.
think we end it now. So I don't know if you want to.